Hey guys, I hope everyone's doing well. This is Tony Bechet, Physics 2C SI for Dr. Anderson. Today we'll be talking about a lot of things, so let's get right into it so this video isn't too long. Um, so the first thing I want to touch on is this law of reflection. So we talked about it last video, but the important thing to keep in mind is that this angle of incidence is the same as this angle of reflection. That's basically the most important thing that you need to know for the law of reflection. Um, if there's an incident ray hitting a surface, it will be equal. The angles will be equal along this normal line. Pretty straightforward. So something that's not as straightforward is this law of refraction. So every time we have a reflected ray, every time we have a reflected ray, there will be some light that goes through this medium. Okay, this is basically what the law of refraction tells us. It tells us the angle at which this ray is refracted. So what is the law that tells us what like the angle in the medium? Uh, Snell's law, written right here. So specifically, Snell's law says that um, the index of refraction for the first medium times sine of the angle of the first medium is going to be equal to n2, the index of refraction for the second medium, times sine of theta 2. Okay, so there are two possibilities. Um, there are two possibilities that can happen when we're thinking about the law of refraction. So as Dr. Anderson's slide showed, we can either have something going from fast to slow, or something going from slow to fast. So what exactly does it mean for something to be fast and something to be slow? So if we look back to what um, the index of refraction is, it is equal to the speed of light in a vacuum, which is given by c, over the speed of light of the in that object. So as this speed decreases, what happens to n? N increases. So something that is fast, something that has a high velocity, will have a low index of refraction. Something that has a slow velocity will have a high index of refraction. So how does this relate to the angle and whatever? So if um, if we have a small n, if n1 is smaller than n2, then that means angle 1 will have to be bigger than angle 2. Okay, so if n1 is smaller than n2, let me change these colors. So if n1 is smaller than n2, that's not right. That means what? That means that theta 1 will have to be bigger than theta 2. So something that goes from fast to slow, this angle is getting smaller. So if theta 2 is getting smaller, what is it doing relative to this normal line? It's going towards the normal line. So, and then you can just apply the opposite to slow to fast. This goes away from the normal. Okay. Now let's talk about total internal reflection. Um, so what is the definition? When an angle is too great, keyword too great, that it reflects the incident light. And what is the incident light? It's this light. It reflects the incident light back towards the medium. So this would be total, if we just forgot about this, if we just cancel this out, this would be total internal reflection. This ray is really getting reflected back into the medium that it started in. And so what is the formula for total internal reflection? We can try to derive it. So we know that n1 times sine of theta 1 equals n2 times sine of theta 2. This is Snell's law. Um, what we really want is so this is the incident ray. This is the normal line. What we're really looking for is an angle so that this right here, this angle according to the normal is 90 degrees. Okay, so we can just plug this in to here and then solve for that. So we get n1 times sine of theta 1 equals n2, and then what is sine of 90 degrees? It's equal to 1. Okay, so then we're really looking for the angle for which this happens. Okay, so this angle happens when theta, we'll call this the critical angle because this is the angle, this is the breaking point between refraction and total internal reflection. So theta c equals n2 over n1, but we need to get rid of this sine, so we'll do the sine inverse of n2 over n1. So now I have a question for anyone watching. Let's say that, so this is n1, this is n2. What if n1, what if the medium, the index of refraction for the first medium, the index of refraction for this medium is smaller than the index of refraction for the second medium? So in other words, what if n1 is less than n2? What happens? Can we have total internal reflection? The answer is no. And we can show this algebraically. We can say that, we can show this mathematically. If n1 is smaller than n2, then this will be greater than 1. This value in here will be greater than 1 if n1 is less than n2, because if we decrease the denominator, we're really multiplying by that number, right? So can we have it? Is there such thing as an angle that will give us a sine of something greater than 1? No. So this is not possible. Okay. So this can only happens when the first medium okay, it's going to be too long to write. When the first medium has a greater index of refraction, when n1 is greater than n2. This is when total internal reflection will happen. It is the only time it'll happen. So what is the difference between the critical angle and this total internal reflection? As we increase this this critical angle, so let's say this is the critical angle. As we increase this angle for the incident ray, then we'll begin to have internal reflection. Then we'll begin to have the incident ray getting reflected back into the first medium. So this is only when this angle is greater than this critical angle. So if a question asks, if a question asks you, when does total internal reflection happen? It is dependent on this critical angle. So we might not have a lot of time for me to go through this, but the way to solve this is to find first. Let's read this together. So a student conducts an experiment to measure the critical angle. The student measures the critical angle to be 52.5 degrees. She then repeats the experiment in a different medium. Okay, so the first thing you need to do is find the medium of this plastic. And I think when I did this, the medium was around 1.26, something like that. Don't quote me on that. Now we know that this new medium, the second experiment, so experiment 2, this second medium is 1.33. Now, what did we just say here? If N1 is less than N2, what happens? There's no total internal reflection. N1 is less than N2. So what do you guys think will happen? Will there be total internal reflection? So I think we can move on from this. So let's talk about dispersion. So it's a little bit annoying. After we were talking about the index of refraction, light, the angle. Now we're saying that the index of refraction changes based on the type of light, based on the wavelength you have. Um, so a good way to think about this is, so this is the spectrum. This is the visible light spectrum. As the wavelength increases, the index of refraction decreases. Okay, so here we have red and blue. We'll call this violet, just to make it easier. So we have two things in the total ends of the visible light spectrum. How does the deviation change based on the type of light that is incident? So let's try to solve for it. We have sine n1 times sine of theta 1 equals n2 times sine of theta 2. Okay, so we know that, let's assume this is air and this is some other medium. Okay, we'll arbitrarily pick this number, but we know it has to be greater than 1. So let's assume that we have 1, and then this angle is, let's say this angle is 30 degrees away from the normal line. So we have 1 times sine of 30. So sine of 30 is equal to 1/2. Yeah. And then we have n2 times sine of theta 2. Okay. So we have 0.5 equals n2 times sine of theta 2. And then we want to check it out for red light and violet light. So we know that red light will have a smaller, based on this, we know that red light will have a smaller, red light will have a smaller index of refraction than violet light. So we'll just say red light has an index of refraction of 1.2, 1.3, and then violet has an index of refraction of 1.5. So then we can solve for this. So we'll say theta of red equals what? It equals sine inverse of 1.3 over 0.5. That's not right. Sine inverse of 0.5 over 1.3. And then theta of violet equals sine inverse of 0.5 over 1.5. And then we get, so I calculated this earlier, we get the angle for the red light will be around 22 degrees. The angle for the violet light will be around 19 degrees. But the thing to keep in mind is that we're trying to understand how it moves away from the angle of incidence. So this angle was 30 degrees. Original angle is 30. Now this new angle, we have 22 and 19. This one deviates more from this original angle. So then we know that violet light will deviate more than red light. Even more so than that, we can say that a higher index of refraction will deviate more than lower, so it doesn't, than a lower index of refraction. So the higher the index of refraction in terms of the wavelengths of the visible light, the higher the wavelength, the less deviation that we have. The higher the index of refraction, the more deviation we have. They're basically synonymous statements. So let's talk about magnification. So we know that if m is greater than 1, if the magnification is greater than 1, we know that this is upright and it's magnified. So this is going to be greater than the original. Greater, bigger than original. And since m is less than -1, this will also be bigger than the original, but it will be inverted because it's a negative. This will be inverted. And we can apply these same rules to this. Negative, so it's inverted, but it's between 0 and -1, so it'll be smaller than original. Okay, so be familiar with this type of terminology because this will be used later. You'll see it later in these slides. So I just wanted to point out the differences between a converging and a diverging lens. The important thing to know, the only thing that you need to keep in mind with this, a converging lens will have a positive focal point. A diverging lens will have a negative focal point. Okay, diverging, negative, converging, positive focal point. That's super important. Keep that in mind because it will very, very, very much confuse you later on when you need to put in these units, these numbers into the mirror equations. So keep that in mind. Converging lens, positive focal point. Diverging lens, negative focal point. Okay, so Dr. Anderson didn't really cover this too much, so I won't spend too much time on it. But if on the exam you need to draw a ray diagram, this is how you do it. So for a converging lens, it's super simple. It's way easier. So we have this image right here. I drew this. So we have this image right here. We have an object. And so we need to draw 3 principal rays. So the first ray goes straight across, and then it goes through this focal point, the far focal point. The second ray goes through the middle, and it intersects this first ray. And then the third line goes through the near focal point, past it, and then it's straight. So we see that this. I'm having trouble hearing. Oh, that's scary. We know that this line, or this principal ray, is the complete opposite of this principal ray. Okay. For a diverging lens, it gets a little bit more complicated. We have this same horizontal aspect, which we had here, except this one goes through the near focal point. So we try to draw an imaginary line through this near focal point. The second ray goes straight through the middle, and then the third ray goes through the far focal point, and then we draw a horizontal line across. And where these 3 lines meet, this is where the image is formed. So this is the object. This is the object. This would be the image. Okay. So this is where it gets a little bit complicated. At least this is what was hard for me when I was first learning this. What do we designate to be positive? What do we designate to be negative? So the thing to keep in mind is that, so first I want to just say this is the magnification equation. So you can take the height of the object over the height. So if there's an apostrophe, it refers to the object. So this is the height of the object over the actual height. This will give you the magnification. And you can also find this magnification through the distance, but by the distance of the object and by the distance of the image. So if this distance of the object, if it's a real, so let me just read this here. If the image or object is real, then it will be positive. So if it's real, it will be positive. This is real, so this S is positive. This is also a real image, so this S is positive, okay? Now, this S over here for the object is obviously a real object. But this image here, this is a fake object, or this is, I don't know if that's the correct term, but it's not real. So then this S would be negative. Okay. So the object is positive here, and the image is negative here. The image is positive when it goes past the lens. So let's try to plug this into the equation. So for a diverging lens, we have S prime is negative over a positive image, and then this will give us a positive magnification. So what does this mean? A positive magnification means this is upright. This is not inverted. This would be inverted because it's positive over, this would be inverted because it's positive over positive times a negative. Okay, so we see that this indeed is inverted, but this gives us a positive magnification, so it'll be upright. We don't know about if it's been made bigger or smaller because we need to know the exact values of these distances. But that will give us the exact magnification. Now, in terms of the focal lengths, it depends if it's convex or concave. So if it's convex, so by the way, these are from Dr. Barton's. These right here from Dr. Barton's slides. This is from Dr. Barton's slides. Just so it's not copyright. So when it's convex, the lens is positive. When it's concave, the focal length is negative. Okay, so convex, positive, concave, negative. Okay, a diverging lens is concave, a converging lens is convex. Okay, so and it's the same sign as the image distance. So based on the image distance, if the image distance is positive, we know this focal length will also be positive. If the image distance is negative, we know this focal length will also be negative. I know this is a mess. I'm so sorry. This is something that I really want to talk about more in depth. I just don't want these videos to be too long. So please, 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 if you're watching this, come to my office hours, Tuesday and Thursday, 2 to 3 p.m. The link is going to be in the description. And thank you guys so much for watching me.